Lesson number 8. During this lesson, I'm going to explain the MPPT and PWM solar charger controllers. So the first type I'm going to talk about is the MPPT, which stands for Maximum Power Point Tracking Controllers. This controller optimizes the voltage coming from the solar panel. So this is the most important point, is optimize the coming voltage or the voltage coming from the solar panels, so the maximum amount of energy transferred to the battery bank. So we will get maximum amount of energy transferred to the battery bank. The maximum power point or the optimal conversion voltage will fluctuate with changes in light intensity, temperature, and other factors. The digital optimization process performed by the MPPT controller find and adjusts the maximum power point quickly. We can see from this curve we have the voltage. This is the output of the solar panel, and we have the current. So you can see the red one. This curve is the relation between the voltage and the current. This point is the maximum tracking point or the maximum power point. At this point, we can see we will get the maximum power. We can see the power start from 0 and the power increase. This is the axis of the power. So you can see the power increase. At this point, we will get the maximum power. So always we want to charge the batteries at this point, at this voltage. So how to get this voltage and this current? The MPPT controller is work to track this point, always track the maximum power point, and then we will get the maximum charging or the perfect charging of the batteries or for the batteries. So how to size the charger controller? What size we need? Once you have sized your battery bank and solar panel array, and I'm going to explain about these 2 points in the next videos or next lessons, determine which charger controller to use. So which type we use, the PPT, or which type to use, the MPPT, or the other type, which is the pulse width modulation, the PWM. This type is the PWM. So which type to use? As I explained in the previous lesson, if we have a large system, we use the MPPT. And if we have a small system, we can use the PWM. After we choose the perfect or the best controller for our system, and let's say we choose the MPPT, now we are going to size the charger controller, which size we need for this system. So to calculate the size, first of all, we know the relation, the power equal the voltage multiplied by the current. Now I want to calculate the current of my house. For example, I have a system. What is the current that this system need? So to calculate the current of the system, we apply the relation I equal P divided by V. V is the voltage of our system. We are going to see in the next example. So a solar array is producing 1 kilowatt. We have a solar array. This solar array produce 1 kilowatt. So it's produce 1 kilowatt and charging a battery bank of 24 volt. So we have the power P of the solar array, which is 1 kilowatt, and this solar system produce 24, or our batteries need 24 volt to be charged. What is the controller size? So which size we have to choose, or which size we have to buy to charge these batteries? If we use a small charger controller, so this charger controller will not work with these batteries because the amount of current of the charger controller will be less than the current that we needed to recharge the batteries. So the size of the controller, it's very important, and how to choose the correct size for our application. How to calculate the controller size? We divide the power, which is 1 kilo, by 24 volt, and we have 41.67 amperes. So our system needs about 41.67 amps. Now introduce a safety margin. So now we have to add a safety margin, because some motors or other devices, when they are turned on, maybe need a current more than the optimum value. Let's say we have a small device, or let's say this is a motor or a small device. This motor, for example, need 1 ampere. But this motor at the startup or the starting point, we need, for example, 3 ampere, just for an example. So the motor need a current like this. It's need 3 ampere, then it will fluctuate about 1 ampere. Okay, so always we need to add a margin because of the problem of the startup of the motors and other devices. So for this example, we can add a margin by multiply the result by 1.25. This means we add a margin 25%. Okay, this is the margin. So 25, if we do some calculation, we'll get this value 1.25. So we multiply the value by the margin or the safety factor. So for this value, 41.67 multiplied by 1.25, we will get 52.909 amps. So our controller should be more than this value. Okay, so in our example, we should need at least a 52 amps controller. So let's see, I made some research from the internet, and I have some charger controller types. So for example, this type we can see from the Amazon, it's produce about 60 ampere. So we can use this type, okay, 60 ampere, or we can use more than this current, but I prefer to use the correct value, because when the size increase, also the price increase. Okay, the price increase too. So the best size is 60 ampere MPPT solar charger. Another type, of course, this one it's say currently unavailable. Maybe in the future it will be available. The other type we can see, this type is 60 ampere MPPT solar charger, and we can see the price. It's about $34.7, and the shipping price is 6.33. So in total it's about $40. So the charger controller cost about $40. The other type of the charger controller is the PWM. PWM is often used as one method of floating charging instead of a steady output from the controller. So what's the meaning of pulse width modulation? Pulse width modulation, we can see the pulse width can be changed. Okay, so you can see when the battery, this is the battery charging, the red color. So now let's say the battery is not full charge. We can see the system provide a pulse width. So we can see this is the voltage. So in this, at this period, the system is on. This means connect the panels. Let's say we have panels and we have the battery here. So connect the panels. Okay, the panels connect to the charger, and then from the charger to the battery. So when we have this one, okay, this width, this means the panel is connected to the battery at this period, okay, and charge the battery. At this small period, we have, or the charger disconnect the panels from the battery. So here we have a disconnection. Okay, so disconnect at this small period. Then after that, we can see the battery is charged. Okay, when the battery get near to the full charge, okay, you can see the pulse width is decreased. Now the battery is more charging, so we can see the battery it's near to the full charge and the pulse width is decreased, and so on. And finally, when the battery is full charge, we can see just the controller send a small width pulses to the battery. So in the next point, it is sends out a series of short charging pulses. Okay, so it's sent pulses to the battery. The charger constantly checks the state of battery to determine how fast to send pulses and how long width. Okay, so this is the width. You can see the width of the pulse. So how long wide the pulses will be. So if the battery is fully charged, it will send narrow pulses, and if the battery is empty or half charged, it will send long pulses. In a fully charged battery with no load, it may just tick every few seconds and then a short pulses to the battery. So you can see here at this part, we can say at this part, the battery is fully charged and there is no load on the battery. So the system, you can see again, in a fully charged battery with no load, it may just tick every few seconds. So you can see just every few seconds, we have here off for 1 second, for example, then just tick on for just a few seconds and send a short pulse to the battery. So in this charging battery, the pulses would be very long. Okay, so you can see this part is discharging battery, and we can see the pulses are very long and almost continuous, or maybe continuous, or the controller may go into full on mode. The controller checks the state of charge on the battery between pulses and adjusts itself each time. So always the controller check the battery. Here we have the battery, and the controller check the battery. If the battery is near a full charge, then the pulses will be narrower, and if the battery is empty or discharged, the pulses will be very long. The downside or disadvantage of the pulse width modulation, beside the disadvantages in the previous slides, is that it can also create interference in radio and TV due to the sharp pulses that is generated. So these pulses or the sharp pulses maybe interfere with the other signals of the radios and TVs. The DC source or the solar panel must always have higher operating voltage than the battery bank in order for current to flow from one to another. So if we have the battery and we have the solar panels and we have the charger here, so the producing voltage, okay, we connect to the battery, we connect the wires to the battery, so the voltage of the solar panel must be higher than the voltage of the battery. For example, 17 volt for the solar panel produce 17 volt, and the battery is 12 volt. So in this case, the current will flow from the high voltage to the low voltage. Okay, so this is very important. Okay, the current flow from the high voltage to the low voltage. So for pulse width modulation controllers, select one that is rated. Now we are talking about how to size the PWM. So for PWM controllers, select one that is rated at your system voltage. Okay, so we need to take the voltage into account. Dividing solar panel array total wattage by the system voltage, we are going to see in the next example how to sizing the solar charger controllers. Add 25% as a safety margin. or we can multiply the result by 1.25. Select a solar controller rated at or above the result in step 3. Now let's see, for example, two 125 watt 12 volt nominal module system. So we have two modules of solar panels, each one 125 watt, and each solar panel is 12 volt. So we connect this system on parallel. So we connect the positive terminal to the positive terminal and the negative terminal to the negative terminal. So this system will produce a 12 volt, okay, because it's a parallel connection, and the total wattage is 250 because 125 plus 125 watt equal 250 watt. Now, how to calculate the current out from this system? To calculate the current, we divide the total wattage by the voltage. Okay, so I equal P divided by V, and we have the result is 20.83 amps. Now we add a safety margin, so we multiply the result by 1.25, and the final result is 26.0375 amps. So which size we have to use, or which controller size we have to choose? So you can use 30 amperes. If we make a research from the internet, we can see the nearest value is 30 amperes solar charger controller, or also we can use, there is no problem, we can use 35 amps, but of course this one is okay, the 30 amps is cheaper than 35 amperes, but we can use both types, there is no problem. In other words, any 12 volt solar controller greater than 27 amperes will work. Thank you.